Okay, how about I take a volunteer to come up and actually enter this in the calculator and do the warm up on the calculator. I'd like to see the stat plot. So, Joshua, are you volunteering back there? No. Yeah. All right, go ahead. It's fun to type buttons on the big calculator. You guys can work together. So see if you can do this as quickly as possible.
Leave it to me.
No, wait.
I know you've already got the calculator. Hopefully, you're just reproducing what you just did on your calculator.
Okay.
And I'm sorry, they're currently covering up the questions as well. So hopefully, if the question will be there. Say it again. I can say it. Yeah, I haven't told you yet. Maybe.
You have what?
Do you want the questions or do you want the data?
We want the question.
Okay.
I don't know how this is gonna work.
wait,
Oh,
how is
just
this gonna-
no. Just cover up this part. Cover up this part.
You guys will figure it out.
Did you finish
Cover
this
up. No, I
problem?
haven't finished it.
Yeah. So this is good. You're going to figure out. Hopefully, everyone coming into today will be able to, with our help here, you're getting a refresher on how to enter data, how to run a regression, linear regression. This is good. Hopefully, everyone knows how to do that. And find the R and R squared value, even though you may not know what those things mean or have forgotten. Right. So we will tell you though again today in a minute. But at least you know how to find them, right? Yeah, you write them down.
37.
Oh, I know.
37.
Faster.
Okay.
33. 24. 29. 26. 22. 24. And 15.
No, by the way, this data makes like no sense. So,
Alright, and then go to.
so we'll just run regression on L1.
Wait,
L2
is diagnostics?
all day.
Alright,
Let's
that's
not
not how you do
like
diagnostics.
Are we gonna go to, this is the old one, my picture messed up.
This question doesn't really make sense to interpret the results, but I think I already have one. That's yeah. Go ahead. All right.
What is turning diagnostic on?
Okay, it's on.
It gives you the R and R squared value.
Graphic. That's a graph.
They should just always do that. I don't know why you have to. Calc, linear regression. There we go. And then type in L1. You know how to do this?
Yeah.
Oh wait, hold up. You just messed up.
I don't know how to do this on this kind of calculator.
I know L1.
L1, L2, and then Y1, right?
Yeah, good. Yeah. So on an old style calculator, like the one I have on the screen, if you have a new fancy calculator, it actually tells you, whatever, X list, Y list, and then store reg equation, and then you can actually put in Y1. Here, you have to do it this way. So that tells run a linear regression with X's in L1, Y's in L2, and then store in Y1 as your equation. So is everyone okay with running the linear regression, doing that too, getting it stored in? Yeah, give it up for Josh. All right. Well done, showing us hopefully stuff you know, but it's good to have a refresher. Remember how to push all those buttons, turn on the stat plot, zoom stat, number 9, make sure everyone knows how to do that. That's a good, nice window for this stuff. Good. Anything else you wanted to say? You saw here too the R and R squared value. So there's your warm up, right? So our linear regression is, if you wanted to round to 3 sig figs, it'd be, here we can write this. Whatever it says there, right? It would be, where does it actually say? Down here? Best fit line. Y is equal to, or is estimated by at least, negative 0.625, excuse me, let's round correctly. 6x plus 45.0. Okay, so is that cool? And then R and R squared values are what are up there. R is approximately negative 0.940. R squared is approximately equal to 0.884. All right, even though you don't know what that means maybe yet, but we will talk about it. Anyone having trouble? Is everyone getting help from a neighbor on how to put the push buttons? I can give you a tip too.
got different values for R.
I don't know what to tell you. You got different value for R and R squared?
I pressed the button very
I don't know what to tell you. Yeah.
What do the R values?
We're going to talk about it today. If you don't remember, I've never learned. Yeah, why would that be? You have these, A and B are all the way the same, all the way down. You have a different R squared and R squared. Did you have a capital R squared? No, you have a difference in your regression. Your A and B values are different. Okay, I don't know. I'm just saying you're actually getting different linear regression, so I don't know what's going on. But okay. All right. Let's come to order. Any questions briefly on the homework here before we move into talking some more about our last lesson today, which is on bivariate data. We'll do that in a minute, but I'll take a question or two on the homework if you have them. How did the normal applications of the normal distribution go for you? In particular, do you okay on the inverse normal question? There's 6, 7, and 8 all required that you do something with inverse normal on your calculator. So, I can say something. Yeah, go ahead.
Could you go over one of them?
Which one is your favorite?
87.
I don't know. Okay, sure. So 7, we're doing something as a study about ocean conditions. It says we've got a normal distribution centered at 83.6, standard deviation of 2.4. Find the temperature that is exceeded 10% of the time. The wording of that question is a little strange, isn't it? So let's be clear. Where are we shading? What are we talking about? 10%. So where is this piece of data? Is this up high or down low? It's up high, right? Because it's only exceeded 10% of the time. That is, it's the 90th percentile, right? Right? Okay, so once that's clear in our mind, we can type in norm on our calculator, in norm. 0.9, you always enter the left tail probability. Okay, is that clear? And that'll give you an approximate value, or and that will be not the value we're looking for, but the z-score that has below it 90% of the area, right? So that will be fine, right? If you want to do it in terms of z-scores, you get a z-score. Something. 1.2816, whatever. Okay, that's the z-score. And then how do you get the? No, we don't normally do this, right? I have a z-score. How do I get back to the x value? Well, if z equals x minus the mean over the standard deviation, then we know all those things. You can solve this equation every time you need it. What would it be? It's always going to be sigma z plus mu, right? We solved that once and for all. So if you wanted to memorize that too, you could. No need to though, right? So what is that? Sigma is 2.4 times 1.2816 plus, in the end, we'll plus 83.6, and then in the end, we'll round this to 86.7 is what I get, degrees Fahrenheit. Okay. You could also do this in one step on your calculator, and that's by doing in norm 0.9, comma 83.6, comma 2.4, and you should get that and just call it a day, right? Does that make sense? People out there? Okay. Yeah, careful on the wording of the question. I think sometimes that's tricky. You're like thinking, so maybe it's not obvious that that's the picture. I don't know. Okay. Yeah.
You guys answer this, but do you want us to write a calculator notation on our equation?
Yeah. Let's see. How would you write this? Let's see. P less than z star or z0 is what I think I said the other day. Yeah, that's the notation I was using on the slide. I'm fine with either. I don't really care. I'm not as picky as that class. I'd like some evidence, that, you know, if you write down an answer and it's wrong, I can't give you, you know how I roll, you know. Okay. I usually give you the benefit of the doubt, but, you know, help me give you partial credit, you know. Okay, so let's start a discussion about bivariate data. We're only, amazingly, we're gonna run through this, and there's lots of content. So once again, I've actually produced the sheet for you that has like word for word what's on my slides, which is good because, like I said, I'm gonna like show you some of these slides for only a second and be like, everyone good? Okay, let's move on. There are certain things that, and again, I apologize to some staff people. You might just, hopefully you learn something today. I don't know. Feel free to criticize what I say if you like. That's fine. You know, help me out. Maybe you'll learn something along the way too. I don't know if I have anything to add to what your knowledge base is already looking like. And maybe there'll be a good review for you too, right? It's always been a while. For those who have not taken stat, some of this I think you know, like you've shown me already in the warm-up, right? Even if you're not taking stat, you do know how to do linear regression, don't you? Right? And you have thought maybe about R and R squared, or maybe you thought even about the residuals, right, before, things like that. So we want to bring those discussions back to mind. If you haven't thought about them before, then don't worry. Okay. Crash course. Everything we will say about bivariate data in one single period. Are you ready? Hold on. All right, we're going to start by thinking about the least squares regression, which is the thing you just did in the calculator. Let me say just one or two words. This is just for your entertainment value. You don't have to write down anything or understand it necessarily. I just want to like speak my piece, okay? How, wouldn't you like to know though? I mean, I'd like to say at least a little bit of where this comes from, okay? So the calculator equation, the task is to come up with two numbers, m and b, right? Once you've determined what those are, you have your linear regression. So what are those? Those are these two things. There are your notes there. And without, that's where the explanation kind of has to stop for us as pre-calculus students. The derivation of these two results, though, is actually not bad once you know a little bit of calculus. It's called the least squares regression for a reason. You take, now I know we haven't said something about residuals, but you take the distance away each point of data is from your supposed line of best fit. You square those numbers, and then you take the minimum over the sum of them. You sum them all up and you take the minimum value. You try to find the minimum value, the thing that would make that the minimum value, given n and b. Right? Try to figure out what n and b should have to be to minimize that. Minimization problems are the domain of calculus. So anyway, but it's not a hard, it's not actually that hard of a minimization problem, but it is a calculus problem. So you have to trust us, calculus people, that this is what, when we do that, this is what that spits out. Everything in these formulas for m and b should be things you understand for the most part. Let's see, mu x and mu y, I know what those are, Mr. Chase. That's, you take the x values and you find their mean. That's this. You find the average of all the y values. That's this. Okay, I got that. You find the standard deviation of the x values. That's this. Square it, or the variance is what that would be in the bottom then, right? So I think I'm good on those. The only one that's a little weird is this mu sub xy. And that's my notation I'm just using here for the following. Take all your x and y values on that table in the warm-up and take their product, the pair, each pair of coordinates, take their product, and then average those. Isn't that what this is? This is the average. That's the mean of the xy data. Okay, so it's the product of the data, the average of those things. And the numerator, this is probably the last time we'll in this class mention the word covariance, but the numerator, mu xy minus mu x mu y, that's called the covariance. So it's interesting, right? The slope is the covariance over the variance, right? Of the covariance between x and y. Sometimes people write it this way. Covariance, x and y, over variance in x, right? That's the slope. The y-intercept is, notice, nice easy stuff you recognize, mu y, mu x. M is this, right? So this is, you could actually write all of that in there. So once you find m, now you can use that to find b as well. Okay. So, like I said, actually not something I'll ever ask you to do by hand or anything, so I just wanted to make sure that, you know, it's math class. Don't we yearn for at least some explanation? I don't know. Okay, and then where did this, what is this and where does it come from? The R value. The R value is also called the Pearson product moment correlation coefficient. Okay, that's whatever. Again, maybe I can't explain fully where the name of that comes from. It's named for a guy named Pearson. There's a product involved for X and Y, right, that is involved, right? Moment, there's something for every distribution called the different moments of the distribution. Anyway, there's a reason, it's the name of it. It's a big long name for R. And here's the formula. Let me put it down here. You guys have all this in your notes, but this should look familiar based on the previous page. Again, the numerator is that like covariance. Mu xy is the thing I described earlier. Okay, so it's very similar, except the denominator is a little different. But this is your R value. And notice now, let's return up to this list and say a few things about it. Notice it's between -1 and 1. And what was it in the warm-up? It was like very close to -1, wasn't it? It was -9 point something, whatever. Which tells me not just that it's a strong correlation, but it's a strong negative correlation. I think even freshmen who didn't come in knowing the stuff maybe the sophomores know have at least talked about that before. You've heard, right? Everyone has heard negative and positive correlation, that idea, what that means. Okay, and then everyone has heard this. We won't discuss this at great length in this class, like at all, but this is a favorite topic to discuss in a stat class too, right? But whatever. The point is, just because there is a correlation in the data doesn't imply causation. In fact, the warm-up is a perfect case of that, because I think I would expect a positive correlation. It doesn't make sense to me that the x value in the warm-up would cause the thing that's still symbolized by the y value. It was like, what was it? Your pay rate, and then like the number of months you stay, and it feels like it should go the other way. So whatever. It did say at the beginning today. Yeah, it's right, exactly. So correlation does not imply causation. This is actually a good case of this. Number of months employed with the company. Yeah, I would think that would be more if you're paid more, right? But this is, like it says here, an example containing fictitious data. So who knows where this came from? Do you like that? I like that. Containing fictitious data. So, disclaimer. We made this up. Okay. There's another value that we care about called the coefficient of determination, which is the R value we just computed, but squared. And AP stat people, and sorry, I for some reason it was not because I didn't want you to have it, but this is omitted notes. I just forgot to, so whatever. This will be on line 2, so don't spend a lot of time writing this down or anything. But this line right here is the thing that I think all of our stat students have to memorize, right? Right. So R squared turns out that when you square this, not only does it become positive, which is interesting, but it also turns out algebraically that it actually does account for the fraction, literally the fraction of the variance in y that is accounted for by x. Okay, or rather by the linear correlation, the linear model that we came up with, right, between x and y. So, I think, what was it, 8.88 or something in the warm-up? Okay, so 88.4% of the variation in y is explained by the linear relationship between x and y from the warm-up, right, is what we'd say. Don't worry about that too much, right? It doesn't matter that much. It's just, again, it's just another measure of how good the fit is. I won't make you memorize or write that necessarily, right? As long as you understand that R values and R squared values close to 1 and absolute value are good. Okay. I think that's good enough for us for now. But what I just underlined, it is true. Okay. So whatever. All right, let's say something about the residual plot. Okay. A residual plot. I've already kind of mentioned this. It's the thing that if you square all the residuals and take the minimum, the sum, and take the minimum best, what gives you the linear regression, the line of best fit. So you already have this data from the warm-up in your calculator, right? In L1 and L2. Does everyone still have it? You didn't clear it out yet, did you? In L3, I'd like to do the following. We're going to actually do the residuals by hand here. There's a feature on your calculator that does it, but we'll do it by hand here, okay? I'd like you to type in the following, and actually, if you actually maybe do it this way, L2 minus Y1 of L1. I think that'd be better than what's here. So that doesn't matter, actually. Both would compute the residuals. They'd just be positive or negative. So the way you type this in is you go up to L3 here, and make sure you're actually blinking, you're actually highlighting L3 and press enter. And then down in the bar, it should say L3 equals blank, right? With a cursor. Actually type this in now. L2, do you know how to get L2 on your calculator? Minus, and then Y1, where do you get Y1? Bars, function, y, right, y bars, y1, yes? And then in parentheses, L1. So what is this actually computing? It's taking the L2 values, which are the actual y value, and it's subtracting from that the value we predict based on the x value and then using our linear model, right? So this is, this comes out to be a positive number. This does, the way I just wrote it here, if our model predicts a value lower than the actual value, right? Makes sense? It comes out negative if our model predicts a value lower. So, I don't know. This is also useful. You could do it the other way, just be the opposite, right? So, if you plot these, you'll get residuals. And actually, like I said, I think this is maybe done the opposite way, so this might be a flip. But it actually doesn't matter. It doesn't matter. Okay, so the thing we're looking for in a residual pattern, because R and R squared, we want to say this in a minute, R and R squared don't say everything about the fit of the data, right? Just because you have a good R and R squared value doesn't mean that, like, you have an awesome model, okay? We also want to, like, take a look at how the residuals are looking, yes? And this is kind of what we're looking for, this kind of thing going on down here, right? We're looking for small residuals, of course, but also random ones that don't, like, have a pattern, right? We don't want any, and this looks that way. This is a little bit of a judgment call, don't you think? I mean, but this doesn't appear to have any systematic error, right? That's the thing we're looking for, right? We'll show you an example in a minute that maybe does have some systematic error, so that's why I asked. All right, so that's called the residual. The residuals. It's good to know what those mean and how to plot them. Hopefully, you guys have yet. Okay, if you haven't, you have this data there in front of you too. So feel free to enter this. Ready, go. Let's do this. We're going to ask the same questions we did in the warm-up, but then we're going to also ask you to look at the residuals. Okay. So again, in L1, put these x values, and L2, let's put these y values, and I will do it with you as well. You have it on your paper, so, or I guess you can look up here. Ah, the pleasant sound of all the clicking calculator buttons. What could be better? We get a good R squared value? You guys are faster than me. I've got this gigantic calculator that I have to push buttons on. All right, I think I entered those correctly. Let's see here. Stat, calc, linear regression, L1. I mean, this example wouldn't be interesting if it didn't spur on some interesting conversation here. Can someone just check and make sure I got my linear regression the same thing you got? Is that, okay, all right. I could have entered the data wrong. You could have too. Let's make sure we all. All right, so that's good. We did the first part of this problem I have for us here, right? Find linear regression, yay. Find R and R squared, yay. And they're good. They're like really good, okay? Right, so case closed, right? Well, yeah, let's take a look at the residuals if you haven't already. Before I go too crazy here, let me just look at this bit too. I just want to see it. Zoom stat. Oh, no, just kidding. Zoom 9. There we go. Yeah, and it looks really good, right? Maybe you can already see some lurking issue though. Okay. Stat, calc. Now. Would you like to just do the residuals with the calculator mode here? Okay, there is a way to get the residuals just without any work. So here goes. Are you ready? When you go to your stat plot, do L1, and then in Y list, instead of L2, let's plot the residuals. And you can actually do it by hand, right? L2 minus Y1 of L1, right? But it also is on your calculator if you want it. It's second stat, resid. There's a list there called resid. So whatever. Anyway, one way or another, let's get a plot of the residuals, please. I'm going to turn off this equation in Y1. I don't want to see it. All right, here's our residual plot. Sorry, I'm getting a little a little bit ahead of myself here. So there's their plot. You guys got the linear regression as well. Okay, and then here's a picture of the residuals, and I have written here something that maybe you see as well, right? So the residuals, maybe this is obvious from the data actually, right? Just from looking at the linear regression, maybe you don't have to look at the residuals, but I think you can definitely see that residuals may be awesomely small, but there is a pattern, a non-random pattern, right? This is like, we have some kind of real pattern in the errors that suggests maybe that this data in fact is not linear, even though this seems like a really excellent fit. Okay. So are you ready to try something? Okay. So maybe it's, here's my suggestion. Maybe it's, how about quadratic, right? Maybe it's quadratic. I don't know. Let's see. You ready? Could it be quadratic? All right. So this is a process called re-expression. I'm going to do something kind of crazy to all of our data. I'm going to take the square root of all of our y values, okay? Can you do this with me? This is like Excel style, right? We've got L1, L2, you've got lists here and here, right? In L3 right now, I don't know what L3 is for you. You have to clear it out. And make L3 be the square root of L2, right? You with me on that? And when you do that, when you define it and press enter, it should compute that for all the things in the column. It's like Excel. It's like a little formula, I guess. Did it do it for you?
Yeah.
If you don't have, if you don't, you gotta do it. You don't have to do it. You're not learning anything? Okay.
Well, I am.
All right, okay. I just want to make sure you're comfortable with the calculator features. If you're not pushing buttons, then I want to make sure, you need to, you're the one that has to push the buttons. So make sure you're good on. Did you get all the square roots?
Yeah.
Good.
How would you store it?
I don't want to store it. Just say yeah, you're gonna do a linear regression. Yeah, and then do a now, ladies and gentlemen, let's do a linear regression for L1 and L3 now, right? And here's what you'll type in. You'll type in linreg ax plus b. Use that command L1 comma L3 comma y1 if you want to store it in y1, or on the new calculators you have a new fancy way of doing it, right? But one way or another, you're going to run the linear regression, but this time on L1 and L3 instead of L1 and L2, and see what you get. Let's see what that looks like. I'll do this too. Is it good? Is it better? Is it? I mean, in particular, what do the residuals look like? I'm interested to know. Boom. There we go. Square roots in L3. Awesome. Okay. Oops.
Bam.
All right, so the first thing we notice is that R and R squared are a little bit better, but that's not necessarily the telltale sign. The telltale sign will be a plot of the residuals. Let's take a look at this too here. Oops. What do I have in my stat plot? Let's make it L1 and L3 just for a second. I just want to see this fit here. So it's even. Doesn't it look linear now? We took the square root of. This is not the data though. Let's be clear. This is x values all the same x values, but all the y values with their square root in instead. It's kind of weird, right? So does that look okay? That looks like a fairly linear fit. Yeah, right.
Just go to second stat and then.
Yeah, let's do that. I'm about to do it exactly. Let's actually look at the residual plot too. L1 versus the residuals. Second stat resid is the name of the list.
We have a lot of extra stuff on these fancy calculators.
You have lots of extra fancy stuff. I know. Yay. Good for you. It's whatever. Nothing you can't do that I can't do with my old clunky TI-83.
We'll see about that.
I mean, you can transfer files. All right, don't start a fight with me. Okay. All right, so that looks a little bit better, right? The residual plot has a little less pattern to it. I think that's more random, so that's good. That's like a little bit of a better residual plot. That's what I'm more excited about than the fact that we have a better R squared values, right? Okay, cool, good, wonderful. Now, then what? What did we just do? Well, we just found the following. If you did the linear regression, you should have gotten this as your answer. Yes? Did you? And okay. Everyone confirm this answer up here is what you got. But that, of course, that is not y equals whatever. That's the square root of y, right? So maybe we square both sides. Yay! Fun. Over here, when we square it, we'll get y, and then over here we'll get something, right? We have a nice binomial. You guys know how to like FOIL it out, whatever. Okay, nice. Actually multiply it out. Maybe use the stored values in your calculator. The values a and b are actually stored right now in your calculator. If you go to stat bars, reg EQ, there are a whole bunch of variables. You can pull up a and b and get those values a and b in all of their full glory, if you like. Okay. Anyway, if you algebraically square this guy, right? We're squaring both sides. You will get some quadratic function, won't you?
Yeah.
Very exciting moment for us. And then also, if you run a quadratic regression, just to compare on your calculator, quad reg L1, comma L2. Try that with L1 and L2. That is with the values x and the values y, just straight up x and y. See if you don't get the same thing. I'm gonna bet that you do. Okay. So, I mean, this is just a process a little bit of showing you again like what your calculator is doing when you're doing quadratic regression. But I would like you to be familiar with this idea of re-expressing the data. Instead of x and y, we've got x and the square root of y. So we can do something to the data, and then afterward we can fix that thing. Is that an okay way to summarize the process? Okay. Maybe x versus root y is linear. And if that's true, then we can like run a linear regression on that and come back and fix our data. So this is good, right? Are you guys happy with this now? We've got a good R value, we've got a good R squared value, we've got awesome residuals, it looks good. Yeah? Oh, R and R squared are just from the calculator, right? You can actually compute them for the linear regression. When you ran linear regression, it should have told you. We didn't write them down here, sorry. But they should be, when you did this linear, did you get this linear regression here, Elisa? No? I'm asking you to do this linear regression up here. Lin reg ax plus b, L1, L3, where L3 is defined this way, comma y1, right? And when you press enter, it should give you the linear regression. If you still have diagnostics on from the warm-up today, it should also tell you the R and R squared value, okay? Try that again. But you should get this value. It's written down in your notes there too, so see if you, even if I, okay, so is everything good? Is everything, oh Ryan, you have a question. Huh? Y1 should be just still the x values, right? L2 is the y values, straight up, x and y, from the example of this. What are we doing, by the way? What is this data from? What are we doing?
Time indefinite water.
All right, so now it says time and depth of water. What if I told you that what we're doing is pouring water out of, or we're draining water out of some urn contains water, right? Is that okay? Would that be fair? That would be kind of somewhat consistent with the data. Okay. Except what's maybe wrong with our model? I mean, we have this awesome model now that we're really proud of, aren't we? But what's maybe wrong? Is there something still lurking? Is this really a good model? Why, from like a higher up perspective, maybe isn't it? Yeah, what do you know, Fonda? Yeah, the future predictions of this model are really, really bold and incorrect, aren't they? You know? Do you guys see what Fonda's saying? That the other half of this parabola doesn't really make sense with our data. So maybe this has been a good experience, doesn't it? Doesn't it? Okay, this has been fun. But maybe it's still not, even though it's an awesome fit, maybe it's still not awesome enough. So maybe we'd have to consider another regression that makes sense with us. Maybe it's something that has some kind of terminating point. It hits zero, or possibly has an asymptote or something at zero at the very least. But having it turn up doesn't make really a lot of sense to me, right? So we're gonna, yeah, Ryan. Oh, you like the fact that I said turn up? Okay, yeah. Sorry.
On the previous slide, why did you do lin-reg for L1 and L2? Did you do L1 and L3 previously?
So I did, the linear regression I did was on L1, L3. Isn't that what you're asking? And then I said, compare that though with the quadratic regression that your calculator gives. Do a quadratic regression on just plain old L1, plain old L2. And see if that gives you the same thing as what happens when we square our, you following all this? If you square our linear regression, it should give you the same thing, our linear regression on L1 and L3. If you square that linear regression, it should give you the same thing as if you do just straight up linear regression L1, L2.
The reason you have regression with like the square root of y, is that the lin-reg of L1 and L3?
That's this one, yeah.
Okay, I did it, I got that as the lin-reg of L1 and L2, not L1 and L3.
Yeah.
Oh, maybe I wrote it up here wrong. Yeah, maybe I mistyped it up here. Okay, let me check that. But the thing I said is still true. Try it, right? If you square the thing that you got, maybe it's not this. Sorry. My bad. Okay. All right. Maybe I just mistyped it. This is linear regression on L1 and L2.
Yeah, that's all.
Okay. Then maybe that's not what we want. Okay. But it should be true that whatever the linear regression on L1 and L3 are, I apologize. When you square that, you should get the quadratic regression on L1 and L2. Try it and see if we're wrong. Okay. So I apologize for that confusion. Thank you for highlighting it, Alan. Okay. I need to say something quickly about this. How else could we kind of have this conversation about data? Well, here's a population model, right? Your first inclination might be, of course, to do it like a linear regression because it looks that way. But of course, you know enough because you're mature, mathematically mature students, that you know that a linear model, even if it is an excellent fit, is maybe not appropriate like mathematically, right? Because again, a linear regression would imply lots of different things that don't make sense. Like over here, back in time, there was a time when the population was negative, for example. Like that doesn't make sense to us, right? So there are a couple things that we don't like about a linear model. One, of course, is the population model that we have kind of our go-to one that we've used many times. Yeah, we kind of already have an experience with this. We already kind of know that it's exponential. So how can we transform this data to be linear, right? I hear you say, if it's really exponential, then we could take the log of all of this, or the natural log, whichever, right? Doesn't matter. Some logarithm would do it for us. And then afterward, how would we fix it? If this data really is exponential, we take the log of it, and maybe it'll be linear. And then how can we undo, what's the opposite of doing that, of taking the log of stuff? Well, you can, yeah, e to the whatever. If you're doing the natural log, then afterward do e to that power. And then it'll fix it, right? Just like we took the square root, and then afterward squared it, right? Same thing works here. This trick can be used in a couple different ways here. Don't go yet. Let me give you your homework. If you have logarithmic data, then you could do the opposite, right? I could add to this list the square root function too, right? The one we just did. Transform your data this way. Right? That's the one we just did. All right, so sorry to go quick at the end there, but I think you have the big picture at least. Your homework is coming to you.
He's the original vacuum in the Peter theory. Peter theory. Peter has a doctorate from the I've never heard of
So bars, fast. What? The last thing I did, so like currently A, B, those are all.
Reassessment. Here's a reassessment. It's the guy that touches.
No, actually, I should be squaring on grade.
I just messed up one question.
Whatever.
Any new like this you get like
And you'll get that back. At least you should. You too, Phil. Hey, take it easy. Good job today.
what?
No, Sam left me. Everyone left.